Let's take a look at another example here. Let's graph the surface and the tangent plane at the point 1, 1 pi over 4 for f of xy equals arctan of xy squared. Now, just as a real quick review, in case you don't recall, please recall, for you, a differentiable function of x ddx of arctan of u equals, it's going to be u prime over 1 plus u squared. So for this case, what we have is u equal to xy squared. So with that in mind, we can go after the partials. The partial with respect to x is going to be, I'm going to write this as 1 over 1 plus u is xy squared, so I'm going to square it, times the derivative of u with respect to x, which is just going to be times y squared. The partial, whoops, one more thing I need to do there. I need to go ahead and evaluate this at the point 1, 1. And when I do, I'll get a half. The partial with respect to y is going to equal 1 over the same thing here, 1 plus xy squared squared times the derivative of u with respect to y, which is 2xy. I need to evaluate this at 1, 1. And when I do, I get 2 over 2, which is obviously just 1. So we have the equation, we can get very quickly here the equation of the tangent plane. Now, I'm going to go ahead and do this with vectors. So I know it's going to look like 1/2, 1, -1, dot, x minus x naught, which is 1, y minus y naught, which is 1, and z minus z naught, which is pi over 4, and set that equal to 0. And what I'm going to get is 1/2 x minus 1 plus y minus 1 minus z minus pi over 4 is equal to 0. So if I solve this for z, I'm going to get z is equal to x over 2 plus y, and then bring all these constants together, and I'm going to have minus 3/2 plus pi over 4. Now, if I wanted to do this without vectors, I know that z minus z naught equals a partial with respect to x times x minus x naught plus the partial with respect to y, y minus y naught. So filling in the blanks, I get z minus pi over 4 equals 1/2 x minus 1 plus, this is 1 times y minus 1, which obviously I bring this over, and I get z equals 1/2 x plus y minus 3/2 plus pi over 4. So again, where is it? There it is. I'm getting the same things. There's two ways to go about it to get the exact same thing. Doesn't really matter which way you use. So now let's jump to Maple and take a look at this and see if this plane makes sense. And actually first, you know what I should do first here? Well, that's okay. Okay, here it is. I need to activate these commands. So I've got D, E, and make sure I don't miss my F. And I have this as D, E, and F because this is continuation of a previous sheet that had A, B, and C already defined. So now let's display it. And this is what I get. Let's make this thing a little bit bigger. There we go. So if I spin this thing around a little bit, I can see that this looks pretty reasonable. I have my tangent plane right here. Looks like I have this point of intersection down here. So this looks like it's going to be a very nice approximation for this surface near this point. Now, just to double check to make sure that this isn't some type of an illusion caused by a maple. I mean, everything looks good here on the graph, spinning it around. I don't see anything that suggests any type of discontinuity. But I really should take a look at that necessary or sufficient condition. And if I go back here, take a look at my partials, and the point that I'm interested in is at 1, 1. Now, look at my partials, and well, I have 1 plus something squared, so this is always going to be positive. This is always going to be positive, as in this part of it. The numerator is always positive, so this is never undefined. So the partial of with respect to x is defined everywhere. I don't have to worry about that. And the partial with respect to y, well, the exact same thing. This component is always going to be positive. This could be negative, but I never have 0 in the denominator, so there's no value of x or y that would ever make the partial with respect to y discontinuous. So the condition is reasonably satisfied that f of x, or the partial of f with respect to x, and the partial of y, the partial of f with respect to y, both of those partials are clearly continuous at this point 1, 1 and anywhere near it. So that tells me that this linear approximation, using this as an approximation, using that tangent plane right here, is a reasonable sort of a thing to do.